Hello, everybody. This is Stephanie Smith coming to you live from NASA's Jet Propulsion Laboratory in Pasadena, California. JPL is the home of NASA's OPALS project. OPALS stands for the Optical Payload for Lasercomm Science. And this is an experiment that we've sent to the International Space Station via SpaceX Falcon 9 rocket in the Dragon capsule. And today is a really big day for the mission. We're very excited. OPALS will be taken from the trunk of the Dragon spacecraft via robotic arm and placed on the side of the station. So this is an exciting time for the team. We've been waiting for this for a really long time, and we're happy to share this moment with you live online. I'm here with Matt Abramson, who is the OPALS mission manager, and he's going to tell us a little bit more about what OPALS is, what they hope to accomplish with the technology demonstration, and what we're going to see online today. So, Matt?
Thanks, Stephanie, and I'm really excited to be here today. We've been waiting for this day for a very long time. We're very excited to get out of the Dragon trunk and head over to our final location on ELC-1 to start doing our optical communications demonstrations. This is going to be a really neat payload. OPALS is a technology demonstration where we're going to demonstrate the new technology of optical communications. So what that means is we're going to try to send data from space down to the ground on a laser or light wavelength, because light that we can see has a higher frequency than radio waves. We can effectively pack more data into that stream than a typical radio transceiver. And so what we're looking to do here is to demonstrate that we can go up to tens to hundreds of megabits per second in our downlink. And that's really an order of magnitude faster than the radio waves we use today for deep space communications. Why this is really exciting technology is because it really opens up the bottleneck of getting data from space down to the ground. For most of us, I can speak for myself on this team. I was born in the 80s, and when I was growing up in the 90s, we were all using modems that were 56 kilobits per second. And now we're upgraded to DSL, and we're getting megabits per second. Well, this is the upgrade for space. We're going to go from kilobits per second, what we're using today on radio, up to megabits per second. So this is a DSL upgrade for space. So we're really excited. What you're going to see today is OPALS coming out of the trunk, using the robotic arm that is commanded from Houston, the same place where they do astronaut operations. And it will take us today to a staging platform, and eventually by Monday we will reach our final destination on the edge of the ISS on the Express Logistics Carrier #1.
Excellent. Okay, so let's go ahead and look at this picture that we've got up now. This is a feed coming from one of the external cameras on the ISS.
Yeah, I think this one is actually coming from part of the robotic arm. So what you're seeing is this is the back end of the SpaceX Dragon trunk. And inside it is the OPALS payload, and that's where we rode up on our way to space a couple weeks ago. And the robotic arm is now inside the trunk, and what it's going to be doing is grappling our payload and pulling us out on our way to our temporary loading platform on the ISS.
Excellent. Excellent. Now, we didn't ride up by ourselves in there, did we?
We didn't, no. We were one of two. The first payload, HDEV, it stands for High Definition Earth Viewing. They were extracted yesterday, and they were actually extracted very quickly. It only took 1 day to do because their final platform is very close to the Dragon trunk, so they required a little less orchestration than we do. OPALS, on the other hand, is way out on the edge of the ISS, so the space station is about the size of a football field, and right now we're at the 50-yard line. So HDEV is hanging out around the 50-yard line. That's their final destination. We're going to be heading down closer to the 10-yard line near the goal zone. And so that takes 3 days. So today, we'll just be extracted from the trunk, put on a temporary platform. Tomorrow on Friday, we will actually be driven on this thing called a mobile transporter. It's like a rail track that goes down the side of the space station. And then on Monday, we will be taken off of that mobile transporter cart and finally put onto our final location on Express Logistics Carrier 1.
Excellent, excellent. So we've got a little bit longer journey. We've got some connections to make in the meantime, but we've got unpacking to do today.
That's right.
Excellent. Let's see here. I think we've got some other shots that we may be able to bring up, maybe a reverse angle from inside the trunk. There we go. All right, so Matt, can you tell us what we're looking at here?
Okay, this is a really great shot here. So what you see on the left, you see that kind of looks like an arm almost. That in fact is the end of the robotic arm on the space station. It is only, it looks like a few inches away from our payload. It's going to grab that grapple hook you see there.
Is that the yellow bar?
That is the yellow bar. It will be grabbing that and taking the payload out of the trunk. What you see on the right side, that is the OPALS payload. So we sit on this about 1 meter by 1 meter pallet. It's called the FRAM, the Flight Releasable Attachment Mechanism. And our payload sits within that. We're bolted on top, and what you're seeing in the foreground is our 2-axis gimbal. And you'll see up on top of the gimbal, there's an optical transceiver. Okay, so that's basically what is sending our laser to the ground. It has one opening for the camera, that's the larger opening, and right above it there's a smaller opening for the laser, and that's where the transmit goes down. So when we do our operations, we'll actually be looking for a signal from the ground that will help us point our laser in the right direction, and then the smaller opening will be sending our downlink signal to the ground. And we actually move pretty fast relative to the ground site, so you're going to see during operations, this gimbal will be moving up to 1 degree per second as it tracks the ground station.
Wow. Okay. And what's next to the gimbal? What's that sort of long, white, bread box looking thing?
So you'll see behind the gimbal, it looks like there's kind of a tank back there. So in fact, it is a tank. We call it the sealed enclosure. And in order to make this to get cost savings on this mission, we had to think outside the box and use commercial off-the-shelf parts, kind of like your standard PC. And to make those work in space, we need air. And so effectively, we have this tank that's pressurized to 1 atmosphere with your just good old mixture of air from Earth. And it has a convective cooling system where it has fans that are blowing around the air inside to cool it, just like your computer has a fan to cool it as well. This really helps us get a lot of cost savings on this mission. And in fact, the laser is in that tank as well. The laser we're using to transmit is in the tank, and there's a fiber optics cable that passes outside the tank, up that gimbal, and you can see the wire going into the back of the optical head. That is where our light signal will be going. In the optical head, there's a set of optics that will set the optics with the right angular properties for transmission down to Earth. And so really, it's an electronics tank. That's where it houses all the brains of OPALS, effectively.
All your avionics are in there, nice and pressurized to 1 atmosphere, just like we're experiencing right down here on Earth.
They feel like they're on Earth right now, hopefully.
And they will be speaking with Earth. So this laser that will be mounted to the exterior of the ISS will be communicating with 1 ground station here on good old Terra.
That's right. We have 1 ground station. It's up at Table Mountain, California. It's in the San Gabriel mountain range. And it's really an ideal location because, number one, it's in Southern California, so we have great weather here. And that's important for optical communications because we can't transmit through the clouds. And so this is really an optimal location because 90% of the days here it's sunny and we have a clear signal to the ground. It's also at a high elevation, so it's up around 7,500 feet in elevation. It's actually right next to a ski resort. And it's where we've actually used observatories there to make a lot of observations of asteroids and comets and even planets. And now we're using it to transmit optical communications data down to the ground. Is
this the first use of Table Mountain for optical communications or laser comm?
The telescope we're using has been, it was built about 15 years ago up Table Mountain, and it has been able to receive some space data prior. However, these have not been JPL transceivers in space. We've received some data from the Japanese and other foreign partners. But this is really the first time that JPL has their own optical communications payload in space. There was one related experiment called LADDI a few months ago, and that was a Goddard run mission. And that went up to the moon, and it transmitted data over laser wavelengths to octal from the moon. Now that's a very different experiment because from the moon, you can see where the moon is in the sky. It doesn't move very fast in the sky. So that's really trying to test out planetary to planetary optical links. What we're testing out with OPALS is kind of a low Earth orbit to ground type of link. You can think of at Mars, if we were to use this would be from the Mars rover on the ground to the orbiter it's relaying with up in the sky. The orbiter, in this case the ISS, moves very fast across the sky. It gets up to rates of 1 to 1.5 degrees per second as it moves. So not only do we have to track the object very quickly, but we have to make sure that our pointing does not have a lot of jitter as we're tracking that object.
Oh, so precision is key with
Precision is key. Pointing is really key to this because the beam is very small, and unlike radio waves, we have to point this very accurately.
So could you equate this to, say, a person with a laser pointer? How precise do we need to be?
So if you're like us across the room from your target where you're trying to point a laser pointer, you're trying to point it at something that's like the width of a human hair, effectively.
But you're not standing still.
You're not standing still. You're walking at a leisurely pace across the room, trying to point that laser. That's effectively what we're doing. When we pass over our ground site, we can only see the ground site for about 2.5 minutes. And so in that 2.5 minutes, we're moving from horizon to horizon. It's a very quick event. And so we have to be prepared for that. Our operations really require that we come in here and we prepare the payload ahead of time, because even being off by a few seconds, if our pointing is off by that much, we won't get the signal.
Now, you had mentioned spacecraft communications. This is a technology demonstration that might not change how we speak with spacecraft that are currently out in operations, but how might it change the way that we speak with future spacecraft?
It really is a game changer in terms of the way we design these spacecraft. Currently, we spend a lot of our effort trying to design methods to buffer data on our spacecraft. Basically, the pace of collecting data has outpaced our ability to send it back to Earth. And so we're trying to collect it all locally on the spacecraft or the rover, whatever's out in its remote space. And we have this very tight bottleneck of sending it back to Earth. And so we have all these strategies of priority of which files we try to collect. And if we open that bottleneck, we can basically take as much science data as we want and send it directly back to Earth. We don't have to deal with designing strategies for storing it locally on these spacecraft. You can also take new types of data, so high definition video. I think we'd all like to see that from the surface of Mars. This is the technology that will make that happen eventually.
Now, Opals will be transmitting HD video, is that right?
That's right. We have a 10-second video on the payload, and that will be sent down to the ground, and the point is to transmit it and be able to reconstruct on the ground such that we don't see any errors in the video, that we can view it.
Fantastic. Now, ballpark, about how long will it be from installation on the station to when we might see that initial transmission?
It's probably going to be about a month. We have quite a bit of commissioning and checkout activities to do. So next week, once we're installed, we'll do our first power on. So right now the payload is not powered on. That'll be very exciting because we have not powered on this payload for several months now. And so this will be the first time we get to see if it's still running and still working for us. Once we get past that step, there's a lot of commissioning activities where we have to check out each subsystem on the payload, make sure it can point, make sure it can transmit the laser, make sure the camera can see the ground. And so there's a lot of coordination activities between the payload on orbit and also the ground station. So that will take about a month, and then we think in early June we'll be downlinking this for real.
Wonderful. All right, so we're going to go ahead and leave up the live shot of the unpacking of Opals from the Dragon trunk. We're going to let Matt get back to check on his team here and the mission support area for Opals. And if you out there watching the show on Ustream have questions for Matt or any other members of the team, questions about Opals specifically, about Lasercomm, about how the technology works or what its future applications might be, go ahead and put those questions into the chat box, or you can post them on Twitter with hashtag Opals. And we'll get the right expert in the room back here to answer your questions live. So we'll check back with you in a few moments. Hey everybody, this is Stephanie Smith coming back to you live from NASA's Jet Propulsion Laboratory in Pasadena, California. I'm in the mission support area for the OPALS project, which today is being removed from the trunk of the Dragon capsule via robotic arm, where it will be placed on the side of the International Space Station. I'm joined by Rob Widoff, a team member, the space station systems engineer, former space station systems engineer on the OPALS project, and he's going to help answer some of the questions that you guys have been submitting via Ustream chat and Twitter. So Rob, first up, so that they know who's answering their questions, why don't you tell them a little bit about what you've done so far for the project?
Absolutely. Well, thank you for the kind introduction, Stephanie. It's a pleasure to be here in the MSA after so many years of work on this project. My name is Rob Widoff. I was the space station and launch systems engineer for the OPALS project, and I had the pleasure of working with all of our partners, including SpaceX and other NASA centers, to make sure that our structural, thermal, electrical, and other interfaces were properly designed and planned for a successful launch, a successful robotic extraction, and later next week, a successful installation and operation on the International Space Station.
Well, it sounds like you are just the man to take on some of these questions, so let's get to it. First one comes from Ted B&H on Ustream. Do you know the frequency of the laser?
Absolutely. So there are two lasers, in fact, that we're talking about here. There's one laser that comes up from the ground, and that's the laser that our optics look for to make sure we're pointing our flight laser in the right direction. The laser coming up talks at about 976 nanometers of wavelength, and the laser that we will return down will talk at about 1550 nanometers.
Okay, so to put that into perspective, because I'm not super well versed in the frequency of lasers, how does that compare to your average laser pointer?
Sure. So our lasers are slightly more powerful than your average laser pointer. They're also not visible by the human eye. So they are near infrared. We can't see them, but when we put the proper lenses on our cameras, we can see them clear as day.
So we're taking a little bit of artistic license in the artist concept that we have on the website that shows a red beam coming down from the station.
Absolutely true. We are presuming that the viewer has a special lens on their eye.
Okay, so no Death Star, no real genius laser popping popcorn on the ground.
As excited as that made us, not this time.
Okay, all right. Moving right along to the next question. It's about the video, the HD video that will be transmitted in that initial test. Will these videos be published for the general public or only to the science team? And this is from Krishna. Well, I can tell you, Krishna, that our plan here in the JPL newsroom is to go ahead and share that video with the world on the JPL YouTube channel. So we will tweet about it, we'll put it on Facebook, we'll share it on YouTube. You can find out more from our website, www.jpl.nasa.gov, and look at all of our social media channels there. We'll definitely keep you up to date on OPALS and all other projects. Next question from Chrisney 1. Rob, how long did OPALS take to make, and how large is the team?
Absolutely. So we started, I believe, a little over 4 years ago, where we had an idea. We had some optical communication experts at JPL that had run some experiments, and we pulled together a core team of 8 to 10 people that have worked since then to fully design and think through and consider the OPALS that we're seeing on the TV today. We spent several years putting the pieces together, and we worked with other NASA centers all across our country, including SpaceX's Mission Control Center here in California, to pull all the pieces together, make sure we could integrate with the launch vehicle and all the hardware on space station. And in total, I counted, we worked with about 350 people outside of our core team at JPL.
Wow, so this really has been a collaborative effort between NASA centers and commercial.
Absolutely. We learned a lot from some of our partners who had run related experiments in the past. We took as much from those prior projects as we could learn, so that we could learn from the design decisions that they had made and make OPALS as successful as possible, which we're excited to see some of those first successful integrations a couple weeks ago at our launch, and today with robotic extraction, which is occurring right now.
Well, it's like Chrisney1 in the chat can read our minds. She wants to know, what was it like working with SpaceX?
Oh, that's another great question. I was the person on our team with the pleasure of working most with them, and they were a blast. They had a really hardworking, really smart team. We were a early career team that started at JPL, and we had some of our peers and prior colleagues that we were able to collaborate with at SpaceX too. Working with SpaceX on this project was especially interesting and I think fun because they were doing a lot of things for the first time. So there were a lot of brainstorming sessions and ideas and explorations of how to do things properly. Some of the hardware we're using that you're seeing on camera today was the very first of its kind that's come out of a NASA and SpaceX collaboration.
Now, this is the first, there's a lot of firsts for us with this. This is the first time we've sent up external payloads in the trunk of the Dragon. It's us and HDEV, OPALS and HDEV, right? That's a big first, and the first robotic extraction.
Yes.
Excellent. Question about that came in. Who's operating the arm?
That's a great question. The arm is operating in a collaboration between the Canadian Space Agency and NASA. So there are ground operators in Houston where we've sent some of our core team members to make sure they have as much input from OPALS as they need to successfully extract and operate our payload today. Those Houston operators are sending commands through our colleagues at Marshall Space Flight Center in Huntsville, Alabama, and they'll relay those commands through our NASA's telemetry and data relay system so that the space station can receive and send those commands all the way out to the robotic arm. So this is really a concert of elements from all across our country to make this possible.
Wow. All right. So if anybody thought that there were astronauts on board station driving the arm, not true. It's being driven remotely from the ground.
Primarily remotely. The astronauts do have interfaces so that they can control this as well. In a nominal scenario, we try to operate this from the ground to leave the astronauts free to operate more custom and critical experiments inside of the space station.
All right, so I'm seeing from our live feed that we're up on a slate right now. Live coverage from the International Space Station will resume shortly. We are in an expected loss of signal period, and maybe Rob, you can fill us in on some of the details about that, about how space station communicates. It's a little different than how we communicate with, say, Mars rovers or the Voyager spacecraft out in interstellar space. Why do we have a loss of signal right now with station?
Absolutely. So the space station can communicate to the ground in multiple ways. Just like the other satellites we design, there's typically more than one way of accomplishing most tasks, and we design that way on purpose. So in case something ever goes wrong or things change on the ground, we still have another way of completing our mission. In the space station's case, there are at least 3 communication bands from S-band to X-band to Ka band, and those are different wavelengths, just like different channels on your radio at home that we can choose to communicate. We use each of those bands for slightly different tasks. One is akin to the old dial-up internet we used to have, which is slower, but we use that to send most of our voice commands. Some of the faster bands are used to send video and to send larger files or data products that will help us bring down and monitor some of the events like we're seeing today. The communication bands like Ka band that we can send video on are dependent on line of sight and weather and orbital access to some of our satellites. Before the space station sends those signals down to Earth, it actually sends them higher up into space to another one of our satellites called TDRS that relays them back down to the ground. The space station can't always see those satellites as it's driving past at 7 kilometers per second in low Earth orbit, and so it often has to wait between locations where it can see satellites to send data like the video we're seeing today.
I'm just going to go ahead and look back in my notes here and see exactly when this LOS is expected to be over. My colleague Courtney here is man in the chat, and let's see. We should be coming back momentarily, and there we are, 11:07. Just as expected, now we've got a shot back inside the Dragon trunk. For those of you just joining us, that's the OPALS instrument there on the right-hand side. And on the left-hand side, that thing that looks like an arm actually is the arm. That's the robotic arm. So
Yeah, so that's a piece of the robotic arm, which has many components to it.
stand by one moment. We've got some activity here in the MSA at JPL, and we'll be right back.
So if you want, I could explain what this arm is called and what it's connecting.
3. Hey everybody, this is Stephanie Smith from NASA's Jet Propulsion Laboratory checking in from the Mission Support Area for the OPALS project. Just to let you know, this mission support area also supports other JPL projects such as NEOWISE, which is out looking for asteroids, and the upcoming Orbiting Carbon Observatory 2, or OCO2 mission. We've got a lot of activities here in the MSA, and we'll need to take our audio down for about 10 minutes. But after that time, we'll be back with more experts from the OPALS team to answer your questions live. In the meantime, you can keep submitting those questions via the Ustream chat box or on Twitter via #OPALS. Thanks so much, and we'll be back in about 10. Hello, everyone. Welcome back to NASA's Jet Propulsion Laboratory, home of OPALS, the Lasercomm experiment that is being extracted from the trunk of the Dragon spacecraft and installed on the side of the International Space Station. So we're looking at live picture from space, from the exterior of the ISS. Now we're switching to a feed inside the trunk of the Dragon capsule. And I'm joined today by Rob Witthoff, one of the team members, who's going to be able to tell us a little bit more about the mission operations that we're seeing right now. So Rob, what are we seeing right now?
Well, thanks, Stephanie. It's great to be back with another look at our payload here. The picture that we're seeing on the live stream from the space station right now is one of three main components. We have the space station's robotic arm system, we have our OPALS payload, and we have the SpaceX Dragon trunk. And we also have on top, if you can see the Earth flying by, as teeny as that is.
That little blue sky there, that is not sky at all, is it?
Right, it's quite the opposite. That is an ocean right off the coast of Africa. So we're traveling at about 7 kilometers per second, I believe over 25,000 miles per hour for those of you that like our unit system. And we are pulling all these pieces together in real time. We've got the whole OPALS operations team sitting behind us in real-time communication with other operators all over our country. For these three main systems we're seeing then,
That's the arm on the left, right?
Yep.
Correct? And then OPALS on the right.
Yeah.
And then the wall behind, that sort of padded cell,
right.
That wall is the trunk of the Dragon capsule.
And that padded cell is what's kept us safe on our way up to low Earth orbit. That is the very top portion of the SpaceX capsule. Just under the SpaceX Dragon capsule is the SpaceX Dragon trunk. And that's where the unpressurized or the external payloads like OPALS and our co-payload HDEV sat on our way to space. After that Dragon was connected to the International Space Station, we have sat on the outside of the space station for over a week now, and this robotic arm that we see on the left has just reached in today to take some initial pictures, and it's now in the process of pulling OPALS out of the trunk. That robotic element that we're seeing is just the teeny tip of a very large component of the space station. As we rotate here, we've got a focused view on the robotic arm. That is called the OTCM, or the ORU tool changeout mechanism. One thing you'll see as we walk through these systems is NASA's had to create a lot of brand new technology and brand new robotics to accomplish out of this world feats like we're doing today. So there will be a lot of acronyms and special names. So
we love alphabet soup here at JPL, don't we?
We sure do. It's a whole adventure.
Even
just learning
OPALS
this
itself is an acronym.
It is the Optical Payload for Lasercomm Science. And so what we see now is we're looking at the SPDM, or the Special Purpose Dexterous Manipulators arm, which is reaching inside with the OTCM that we saw earlier to grapple a part of OPALS. This SPDM component, or the Special Purpose Dexterous Manipulator, is very much a special purpose component. This sits on top of the main robotic arm on the space station, and it has two arms of its own. It's almost humanoid in how it can reach in with these two arms. It can grab something with one hand, pull it out of the trunk like we're going to do today, and put it on another arm or another side of the SPDM that we may see with the larger shot. What this grapples onto that we're seeing in this image now is a part of OPALS called the FRAM. A FRAM on the ISS is something we've liked to think of as a Lego block that we have at home.
Really special.
A special metal,
expensive, fancy space Legos.
About as fancy as they can get.
Okay.
And where they draw a parallel to Legos is there are all sorts of places on the ISS where these FRAMs can be connected. We've selected a part on the left, or the port nadir or Earth-facing side of the ISS, where we're going to connect our FRAM to another FRAM component where we will click in. There are many places that we could click in, but we've designed our laser and our system to work especially at that one location.
And it's very important that we have that line of sight transmission, right? So if we can't see it, we can't speak to it.
Absolutely. With laser communication, it has the potential to communicate faster than traditional radio comm, and it also uses a lot less power. But with the color or the wavelength of light that we're sending, if there's a cloud between us and our station on the ground, we won't receive anything. So that type of moisture will block our signal. And because of that, we have to be positioned on the lower or Earth-facing side, of course, of the ISS, and we can only talk to the ground when we have relatively clear skies.
All right. So we see the robotic arm reaching into the Dragon capsule here, grappling opals. After this, what are some of the next big steps in the installation process, and about how long is that going to take? We had a question in the Ustream chat about that, so wanted to make sure that that gets answered.
Yeah, what are some of the next big steps? We've been planning for this extraction for several years now, and we've got some really fantastic operators in Houston and in Huntsville at the other NASA centers, and also at our Canadian partners, the Canadian Space Agency, who have been working to make this possible. What's happening right now is the robot arm has just placed itself on top of its connection point on opals. We haven't yet rotated and started to extract. We're checking our connections to make sure everything is ready to disconnect now. Later today, we will be pulling opals after this arm is fully latched on. It will rotate a drive mechanism inside of the opals FRAM connector, and it will lift this out and take it outside of the Dragon trunk. And that's when we've finished our integration and partnership with SpaceX, and we're ready to move on to our operational part of the ISS. What we'll do, however, though, is we can't sit outside in space without power. It's very cold out there. And after this arm of the space station's robotic system pulls us out, on another side, perhaps on the robot's shoulder, it has another FRAM that it can click us into, and that will give us heater power so we don't freeze, so we don't get too cold. And that's how far we're going to take this today. What we'll do tomorrow and on Monday is we'll then move to another robotic transporter, which will slide us all the way down to the other side of the ISS, and a robot arm will then pick us off of the slider, or the MT, the mobile transport system, and connect us to our final resting place at that Earth-facing side of the space station. And that'll happen on Monday. Once we're connected on Monday, that's when we've connected to our power lines and our data lines, so we can send commands just like we can send data over the internet through the space station's communication system. We'll send commands to turn heater power on first. We'll then turn our computer on and start talking to our computer to make sure that things are checked out okay and things are healthy, so that we can continue towards hopefully a successful laser communication demonstration in the next several weeks.
Excellent. So it was mentioned a little earlier in the broadcast, the ISS is a really big place. If you were to hover it over an American football field, it would take up the whole field. And so where we're at right now, we've come in at the 50-yard line, and we've got to get down to the 10. And that's where that mobile transporter will really help us make the connecting leg of our journey.
Exactly.
Excellent. Okay, so everyone's been so patient in the chat. Let's go ahead and get back to some of your questions. All right, here. Dun, 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 dun. We've answered, let's see, quite a few. There we go. Chi-Town Chicas wants to know, if OPALS works well, will more than one receiver station be established? So what might be potential next steps if the technology demonstration is successful?
Yeah, that's a great question. That's something we've been really excited about. With optical communication, just like other forms of comm, you're not limited to one ground station. As long as you have the right hardware on the ground to receive, remember that special color or wavelength of light that we're sending, we can receive that from anywhere that we can point and successfully point our laser to. After a successful demonstration with our primary ground station, which is here at Table Mountain in California, we are hoping to attempt another successful downlink to another ground station. That would be a stretch goal for us. Our primary goal is to demonstrate that this is possible to California. We will use OPALS to learn as much as possible about this technology, the ability to send light through our atmosphere, and what that's like when it's received. Future generations of OPALS will potentially be more flexible to more ground stations and more data and more places to operate both on Earth and not just on the space station, but on more spacecraft in more places throughout our solar system.
But it is important for folks to remember that this is very hardware dependent. So it's not going to change the way that we communicate with, say, the Curiosity rover at Mars or Voyager now out in interstellar space, that those have established radio frequency communication that they will continue to use for the durations of their missions. And what we're demonstrating with OPALS is something that is a potential technology to change the way and that really open up the data rates for future spacecraft.
Absolutely. We've had some world-class experts at JPL studying optical communication for tens of years, and some of the work, the groundbreaking work that they've done showing that this is possible and with early demonstrations is leading towards letting more missions bring home more data.
More data is what we want. Our science teams are hungry for it, and that's how we learn. All right, let's see. A specific question now. Mark said in the Ustream chat, asks, the laser may be coherent, but it still spreads in a beam over distance. How wide is the beam spread from source to target? I've heard it's pretty wide by the time it gets to the ground.
Yeah, by the time that laser gets to the ground, it's on the order of multiple hundreds of meters. And so our job is to make sure that that laser, the hundreds of meters that's visible for, that the telescope we're pointing to is somewhere inside of that circle.
Right, but it is still, it's still a very precise maneuver, right?
Yeah, extremely precise, much more precise than typical radio frequency. Just like when you're driving in your car, you can turn on your FM radio wherever you are on the road. We don't have quite that flexibility when we're using optical communication.
Okay, going back to your questions from the chat, Flight Ian 1, where are those cameras located from that we're looking at right now? So let's go ahead and look back at the live shot here, Rob.
Oh, awesome question. These, there are two, perhaps three types of cameras that we consider here. The cameras we're looking at right now are cameras that were built inside of the SpaceX Dragon trunk. There are several cameras in here that were designed to monitor and help guide the robot arms in and to make sure that our components were healthy and that video was available for us to look at before we even sent the robot arm in. Some of the other feeds that we have, the robot arm has several cameras of its own that are active now, and we're using that telemetry to guide this in and make sure we have a precision alignment before we connect or take anything out of the trunk. And the last type of camera that we'll use a little bit later in our mission are from the crew members that we have inside of the space station. They have a fleet of very high quality imagers and cameras, and they will look out their windows when they have a chance, and we'll arrange for time for them to take a picture of OPALS of high quality that we can look in high detail to make sure things are safe and healthy and in one piece. And we'll take advantage of all these systems to make sure we're a success.
Wonderful. Now the shot we're looking at right now, this is from an external camera on the exterior of the ISS. It's pointed back at the Dragon. You can see into the trunk there. The Canadarm2 is reaching into the trunk, and it is in the process of grappling with OPALS. Now this is a very slow and deliberate process. We've only got one OPALS, right? We've only got one Dragon up there at station, and we've only got one station. So we want to make sure that we're very careful. And again, a huge thank you to our colleagues at Johnson Space Center who are maneuvering that arm right now. So no astronauts are maneuvering the arm. The astronauts are having other activities today. And this is being controlled remotely from the ground. We really love robots here at JPL, don't we?
We do. We've used them for quite a few things, not only at home in low Earth orbit, but on several other planets as well.
Going back to your questions. Ooh, Lewis and Quark, love the handle, wants to know what's the average power of the ground-based and space-based beams?
They're less powerful than I would have guessed. For the actual numbers, I'm not sure those have been shared just yet. We will likely be releasing those in future publications.
So stay tuned to www.jpl.nasa.gov, where you can get all kinds of information both on OPALS and all of our other 20-plus flying missions and instruments. Going back to your questions, I think we've mentioned this one before. I think Rob, you've touched on this, but it is a consideration and it's worth addressing. Lemon 220, are the lasers disturbed by the atmosphere?
Absolutely, and in fact, quite a bit. When we were designing and when our science team was designing not only the optics, but the wavelength or that specific color of light that we chose, those were designed and selected with enough margin to make sure that in a worst case average scenario, when there is excess moisture and content and other
clouds. These
clouds.
are fancy words to say clouds and fog.
Yeah, clouds
Okay.
and fog. That's an easier way. When that's present, there's going to be some dispersion of that light. So it won't take a perfectly straight path from space to the ground. And so we've designed our beam to be wide enough and powerful enough so that even with a little bit of dispersion, our scientists still expect that light to make it all the way to our receiver so we can receive that data and show that this technology is functional in our project.
All right. So we're going to let Rob get back to the team. And if you've got questions, please, please, please put them into the chat window at ustream.tv/NASAJPL2, or you can submit them via Twitter using the hashtag OPALS. Thanks very much, Rob. And everyone, we'll be back in a few minutes to answer more of your questions and to update you on mission operations at the ISS with the OPALS extraction. 3. Hello, everyone. Thanks so much for joining us here at the NASA Jet Propulsion Laboratory, home of the OPALS project, which today is being taken out of the trunk of the Dragon spacecraft, which is currently docked with the International Space Station. And OPALS will be installed to the side of the space station, headed for its final destination, where it will be moving on Monday. I'm here in the mission support area at JPL with the mission manager, Matt Abrahamson, and he has agreed to answer some more of your questions from the Ustream chat and from Twitter. We're taking questions at ustream.tv/NASAJPL2 and on Twitter using the hashtag OPALS. So, Matt, without further ado, let's get back to these questions. Okay. A lot of people in the chat are asking, and I think this is something you answered at the top of the broadcast, but as people have joined, they just want to know, how long is today's process going to take?
Yeah, it's actually a very long process. Unlike the other payload that rode up with us, HDEV, we actually have to travel long ways to get to our final location. So I made this analogy earlier, but the space station is about the size of a football field, and right now the SpaceX Dragon, where we're sitting, is about at the 50-yard line. The payload that took out yesterday, HDEV, its final destination was around the 50-yard line, so it only took 1 day to take out. As opposed to us, we're going down near the 10-yard line on the football field, so it's actually going to take 3 days of robotic work. So today is just the first of 3 days. We will be extracted from the Dragon trunk today and temporarily stored on the outside of the space station. Tomorrow there's a mobile transporter that will take us from the center of the station out to the edge on a rail line. So it's almost like a train or a rail track on the ISS. And then on Monday, the arm will come down with us and they will extract us from that rail to put us on our final location on ELC-1.
Well, how long does today's extraction? So this broadcast is going to focus on extraction, which is a fancy word for unpacking, technical word for unpacking. So we're reaching in with the Canadarm2 to grab the OPALS instrument and pull it out. It is 12:10 p.m. Pacific time right now, and how long does this window of operation go through till?
So the nominal window of operation goes through the end of the day, so we're expecting early afternoon we'll be taken out of the trunk, so that could be in the next couple hours. And then there's a 4-hour window for getting us to our staging location. During that time period, power will be removed from our payload, so that's very important for us because there are heaters keeping us warm. We're up in space, it's very cold. And so once those heaters are deactivated, we have a certain limit of time we have until we need to be powered again to warm us back up. Today, that limit is about 10.5 hours. And right now, you can see the arm is attempting to grapple the OPALS payload. The heaters are still on at this point, but we're getting very close to the point where they will disable the heaters for the first time. At that point, we'll start a clock. And from that point on, we have 10 hours to get to our location. We expect it to be about 5 or 6 hours.
Okay, so we're going to another shot from one of the robotic cameras inside the trunk of the Dragon spacecraft. Matt, why don't you just walk us through what we're seeing right now?
Sure. So on the left side of the picture here, you're seeing the robotic arm. That is the end of the arm. It's called Arm 2. There's actually 2 arms that this Canadarm can use to grapple the payload or whatever it's using. So it's kind of like having your own 2 arms. You have one you're grabbing the payload with, and the other one is free to do whatever else needs to happen with the robotic arm. It is grappling what the payload is sitting on. That's called the Flight Releasable Attachment Mechanism, or the FRAM. And so our entire payload on the right side is bolted to that FRAM, and what you're seeing is the robotic arm on the left is grappling that hook. Once it grapples that hook and connects, they will call the SpaceX Mission Control in Hawthorne, California, ask them to remove heater power to the payload. At that point, they will demate the OPALS payload and bring us out of the trunk. At that point, we'll be floating high above the Earth. I'm really looking forward to that.
So I don't know if you guys noticed in the close-up shot from inside of the trunk, you can see the Canadian Space Agency logo on the end of that robotic arm. And our friends over at the CSA, there it is, right there on the left-hand side of your screen. So the Canadian Space Agency was kind enough to tweet a video showing a computer simulation of the activities that are happening today and those that are planned for tomorrow and then for Monday, showing OPAL's full transfer via the Dexter unit I love that it has a nickname. This is the nickname for the end of the arm, correct?
That's right, yes.
Okay, so Dexter's coming in and going to get our opals. And so if you don't have hours and hours to sit with us here and watch our very meticulous process of extraction, you can get the accelerated version via this short YouTube video. We retweeted that from the JPL Twitter account. So if you go to twitter.com/NASAJPL and look at our most recent tweet, you can see that video for yourself. And we may even be able to roll that later on in our broadcast today. But stand by, we've got lots more to show you, both from the robotic cameras on station, and we've got lots more to tell you in answer to the questions that you've posed. So let's go back to those questions now. All right, Matt, next up, this one is from Helix 111. Are there any more projects like Opals being worked on at this moment or in the near future?
That's a great question. In fact, there was a spacecraft a few months ago called LADEE. It's an experiment that went up to the moon, and it had an optical communications terminal on it. So from the moon, it transmitted data back down to the Earth to the same ground station that we are using in Table Mountain, California. And that experiment was similar in some ways to Opals. It was still transmitting over a laser wavelength or an optical wavelength, but it was also different in the fact that the pointing requirements are much different from the moon. The moon is fairly fixed in the sky. We're going to be on the ISS in low Earth orbit, and we pass across the entire horizon in about 2.5 minutes. So we need to point very accurately and track very accurately, where we're going to be slewing our gimbal to point this laser at speeds up to a degree per second.
Wow. So for anybody who's seen an ISS pass, you know exactly how fast it travels across the sky. And if you've never seen an ISS pass, it's something that I would highly recommend. Personally, I think it's just very cool to see this bright light in the sky that looks like a little star, but it's not a star at all. It's the International Space Station, and there are people on there, and there's a ton of science on there. And as of today, there's a new JPL Lasercomm experiment on there. If you go to www.nasa.gov/ISS, you can find out more about the International Space Station, astronauts on station, the ground track of where the station is passing over the Earth right now, and also sign up to get alerts telling you when the next pass that you can see from your backyard is. So www.nasa.gov/ISS. Okay, back to the questions. Ted, B&H, wants to know what size mirror is being used to gather the laser light on the Earth station end of this demo.
So the ground station is called the Optical Communications Telescope Laboratory. It's up on Table Mountain in the San Gabriel mountain range in Southern California. And the mirror we're using is a 1 meter mirror. It's 1 meter telescope. And it's really an ideal location for a ground station because, number one, it's in Southern California. We have fantastic weather here. And an important aspect of optical communications is we cannot transmit through clouds. So we need a direct line of sight to the ISS. And out here, we can speak for today, it's bright and sunny, and it's a great place for optical comm. The other aspect is it's at high elevation. It's at about 7,500 feet above sea level. And so we have fewer atmospheric turbulation effects up at that level.
So let's go to Krisney's question, another great question. What was the most challenging aspect of building Opals?
I think it's the list of firsts. So Opals is really a trailblazer in a lot of aspects for JPL. This was our first payload going on the SpaceX Dragon capsule and the SpaceX Falcon rocket. This was the first external payload built by JPL for the space station. It was our first space terminal performing optical communications that we sent up into space. It was the first flight of the particular SpaceX Dragon Falcon rocket we were working on. So I think that was really the main challenge, was trying to get all of our interfaces to SpaceX and also to Marshall Space Flight Center and Johnson together for this coordinated effort. It really is a coordinated effort, and I think JPL hasn't really worked a lot with the other NASA centers in the past, and on this mission we really are. We've been working with a lot of them.
I think there's been lots of collaboration, and I'm very happy to see all the collaboration today. Again, the robotic arm that's extracting the JPL payload, that's being driven by folks at Johnson Space Center, and the communications are going through Marshall Space Flight Center. So we've got lots of collaboration and coordination on the ground between various NASA centers around the country, and we're very happy to work together and get this payload onto the space station so it can start doing some science. So, question about safety. So, Lenco 2400 asks, is the technology safe for pilots? The illumination of the laser beam. I know that they always tell you, don't point your laser pointer up at the sky because you're going to blind a pilot. And we've got a laser from the International Space Station. What are our safety considerations?
Yeah, that's a great question. So we have two lasers, one from the ground station pointed up at the ISS and one from the ISS pointed down at the ground. For the laser being pointed up at the space station, there are not any laser safety concerns based on the power level of that laser. By the time it would hit an aircraft and reflect off many surfaces, it would not be powerful enough to harm that pilot. Now for the space laser, that laser is at 2.5 watts. That is a hazardous laser. So we have to be concerned about astronaut safety.
For those at close range?
At close range. If the astronauts were outside of the vehicle on an EVA or extravehicular activity, they could be in harm's way when our laser's on. So what we have worked out with Marshall Space Flight Center and Johnson Space Flight Center is a series of inhibits or restraints on our laser to ensure that we have two-fault tolerance to be off at all times the astronauts are outside of the vehicle, whenever the robotic arm is within our field of view. And we've also restricted our pointing field of view so that we cannot illuminate any part of the ISS structure with our laser.
Excellent. So there are safety officers working on this, and the utmost caution has been taken to make sure that OPALS can do its science in a safe way.
That's right.
Excellent. So Owl Lady 1 asks, what's the ultimate purpose of this laser beyond the demonstration?
Well, the purpose of the laser is for the demonstration. It really doesn't have any other purposes beyond that. This is a very focused technology demonstration. And so the purpose of this is to downlink data to the ground. This is not any sort of weapon or any other sort of technology we're demonstrating. It is communications solely for the purpose of transmitting data.
And it's also not a new communications portal for the ISS. For example, the ISS won't be sending science via this laser.
That's a great point to make. We are demonstrating a technology for NASA and for JPL of learning how to use optical links and trying to record how often they're reliable, how often do we have to deal with atmospheric turbulence effects, how reliable is this optical link. And so the more we can practice with this, the better we'll be in the future for building a similar terminal for Mars or beyond. And so this is really the first step, but that's a good point. It is not operational, it is a technology demonstration. We're doing this to learn about optical communications.
A lot of great things come out of technology demonstrations, so we've got to do that first before we can go on and put them into practice for science payloads in the future. Right, and let's see. From Twitter, let's go ahead and take a question from Twitter. At Christy Marshall, what views do the arm operators have while operating their arm?
That's a great question as well. You'll see that there are a couple views on the Ustream that are handing back and forth. Currently, there are 3 camera channels being streamed out of the Dragon trunk. So when the Dragon launched on the SpaceX rocket, they had 3 cameras positioned there, and now you're seeing one of them that is positioned right in front of the OPALS payload. There are also several cameras on the robotic arm, and so the previous image you were seeing was coming from the elbow of the robotic arm. There are also cameras on the very tip end of the arm, as well as on the body of the arm. Later on, when OPALS is extracted from the trunk, there are cameras that are on the body of the space station on the P1 and S1 trusses. And so once we get out of the trunk, those camera views will give us a better perspective of the robotic arm relative to the station.
Excellent. Okay, well, thank you so much, Matt, for taking on all of those questions. It looks like we do have a video that we'll be able to roll for you in a few minutes. But first, I want to go and get an expert who will be able to talk you through what you're seeing in that video. So thanks again, Matt. For those of you listening and playing the home game, if you have a burning question that has not yet been answered, please post it in the Ustream chat or on Twitter with hashtag Opals. Thanks so much, and we'll be back in a few minutes. Hello, everyone. Thanks so much for joining our live stream from NASA's Jet Propulsion Laboratory of the OPALS instrument, extraction from the Dragon trunk and installation on the side of the International Space Station. This is Stephanie Smith from the JPL Newsroom. I'm coming to you live from the mission support area of OPALS at JPL, and I have with me Rob Widoff. He is the space system engineer. Help me out here, Rob.
Space Station Systems Engineer.
Excellent. For the OPALS project, he is going to answer a few more of your questions. We're coming up at the end of our regularly scheduled broadcast. Our show will go through the top of the hour, 1 o'clock for those of you with us in the Pacific time zone, 4 o'clock for Eastern, and 2000 hours in UTC GMT. So we'll answer a few more questions, and then we got a very cool video from our friends at the Canadian Space Agency that Rob will speak to, and it will show you the maneuver as planned for extraction and installation. So back to those questions. Rob, what's the difference between demonstrational and operational? This goes back to a conversation we were having earlier.
Ooh, that's an important distinction. At NASA, we have a concept of maturity of technology, and ideas are at the lowest maturity level, but they're important. And we'll take ideas up through concept to prototype to pilot, all the way up to eventually operational technology that we're comfortable sending out to our next Mars rover that we're working on for Mars 2020. Or similar, wherever that takes us. And so a demonstration of what we're looking at for OPALS is to demonstrate that with commercial grade avionics, we can successfully achieve optical or laser communication from space to the ground. And that demonstration means we're looking to show that it's possible, and we're looking to learn about any quirks or peculiarities of how we need to make that possible. Operational technology will come later. That's a future step for a future project that we're paving the way towards.
Excellent. So it's important to define that this is a demonstration on the ISS. It's not operational for the ISS. Science data from the ISS is not going to come back down to the ground via OPALS.
Right.
So the initial question here came from Ben Owen, 1712. Thanks, Ben, for that question. And I think that this answers Mark Sed's question, which was, what will the improvement in bandwidth mean for folks that enjoy live video streams of Earth's views from space? We won't be broadcasting in that way, but there is another payload, HDEV, that will be broadcasting those views. So Mark, go ahead and check out HDEV for some new views of Earth from space, and particularly Earth from the International Space Station. So Lewis and Quark, our friend from the chat, back with one more question. Do you have to make any adjustments each time the sun rises and sets for the ISS?
Each time the sun rises and sets, yes, there are several adjustments that are made, some automatically, some mechanically through our commands over each pass. As the sun rises, there's more heat that's going towards the space station. That means the solar panels can receive power. It means the solar panels heat up. You'll see at the center of the solar panel truss, for instance, there is a small metal truss, and each side of that truss, as that heats and cools, it will expand differently. So the actual structure of the ISS is built to flex and change as that heating changes. For OPALS, depending on the pass, we will have different optical properties and different amounts of noise that we're trying to see our light despite. When it's light or bright out, there's going to be a little bit more background noise or other light in our wavelength, and we'll need to filter that out. We may operate a slightly bit better at night when there's less noise, and that's actually one of the areas that we're looking to collect more information to see what impact that has on our ability to successfully communicate.
Okay, so you mentioned the ISS, you mentioned Opals. Let's go ahead and take a look at the video that shows both, as well as the Canadarm, going through the planned maneuvers of this operation. So we're going to go ahead and roll that video now. And Rob, would you explain what we're seeing?
Sure. So this shows a carefully orchestrated maneuver where what we're working on today is that OTCM reaching into the SpaceX Dragon and pulling Opals out. After we've been pulled out, we're not plugged into a power source and we get cold quickly. So the first thing we do is the SPDM swivels its shoulder around and connects Opals onto another device called the EOTP there. And that's that FRAM LEGO connector we spoke about earlier. After Opals is heated and connected, the robotic arm puts Opals down and connects to another part of the space station so that it can grapple the SPDM from another angle, and it's going to swivel over so that we're closer to our final install location on the Earth-facing side in a place called the ELC. That left arm is then going to reach in, it pulled Opals off of the EOTP again, and this is the final install location for Opals. So now we've clicked in, we're on the Earth-facing side of ELC1 on the left Earth-facing viewport, and we're ready to operate. So that's the ride the robotic arm gives us, and we're very thankful for the integration so we can get to our home without having to send astronauts out and start laser communication.
Excellent. Well, things are busy here in the mission support area for Opals at the Jet Propulsion Laboratory, and we need to let Rob and Matt and the rest of the team get back to their regularly scheduled duties. That will do it for our live broadcast today here on ustream.tv/NASA JPL2. Thank you so much for joining us for this portion of the Opals mission, and continue to get news about Opals, about integration, about the project, and about everything NASA's doing at www.nasa.gov. Thanks so much, and goodbye from the Jet Propulsion Laboratory.